So this is my project for KSP. What is KSP? It's an expression for slightly soluble salts for an equilibrium reaction. When dealing with KSP reactions, you take the coefficient in front of the ion and raise it to the power of that ion. So for example, the B coefficient in front of the X will be raised to the power on the X when making the KSP equation. Same for the C coefficient in front of the Y. It will be raised to the power of the Y ion. This is just a picture showing the layout of how every KSP equation should look like from here on out. This is a real example of a KSP problem. You see the dissociation of lead-2-sulfate into its ions, lead-2 plus and sulfate-2 minus. Since there are no coefficients, the KSP equation can be written in equal amounts. Because of this, each ion can be represented as an X when looking for the concentrations of these certain ions. But in other problems, you might have a 2x squared or a 4x or whatever the reaction calls for. What are we solving for? When the problem gives us KSP, we're solving for the concentrations of the ions. To do this, you would need to change the ions to be represented as x's and divide to do simple algebra and get x by itself. On the other hand, whenever we're given the concentrations and we're looking for KSP, we would just plug in the concentrations to our KSP equation and solve from there. So for example, we're given a KSP problem and it gives us the KSP of magnesium fluoride, which is 8 times 10 to the negative 8th, and we're asked for grams of magnesium that would dissolve in a 0.25 liter of water. So first write the BCE, which is magnesium fluoride yields Mg2 plus and 2F minus. And then write the KSP equation, but don't forget to put the 2 exponent on the fluoride since it has a 2 coefficient. We can set this equal to 8 times 10 to the negative 8th because in the problem it told us that was the KSP value. Next, change the ions to x's. So magnesium gets an x and fluoride changes to 2x squared. The 2 is still in front of the fluoride because we still have to keep the 2 coefficient in front of the fluoride as well as the exponent. Combine the x's and solve to get x by itself. Next, do stoichiometry to find grams. So we take the molarity that we just solved for and get to moles by multiplying by the 0.25 liters. Then we do mole-to-mole ratio of magnesium to magnesium fluoride taken from the BCE. So it's just a 1-to-1 ratio. And then from there you use molar mass to get to grams. So you multiply by 62.3 grams and you get a final of 0.05 grams. Also with KSP there's the common ion effect, which is when the reaction is forced to be less soluble whenever a common ion is added to a solution. So this means that whenever NaCl is added to this problem, it would shift left because of Le Chatelier's principle. And whenever it shifts left, it shifts to PbCl2 to reestablish equilibrium. So since more reactants are formed, PbCl2 becomes less soluble since it's sharing its solubility with a common ion, which is chloride. So this is a picture demonstrating the common ion effect. Both beakers originally contained PbBr2 solutions. In the second beaker, CaBr2 was added, and it increased the concentration of Br-. So it caused PbBr2 to precipitate due to the common ion effect, making the PbBr2 less soluble. This is a chart to show common soluble ionic compounds and some insoluble ionic compounds. Also, in case you forgot the solubility rules, they are Cash and Gia, which are the soluble ones, and CHOPS, which is insoluble. Cash and Gia is chlorides, acetates, sulfates, halogens, nitrates, and group 1, and ammonium. CHOPS stands for carbonates, hydroxides, oxides, phosphates, and sulfides. Also, there are some exceptions to memorize also. Well, that's KSP. Yay!